So where we ended Wednesday was we looked at these two reactions, and we noted that when they go through and form the reaction, that we get different products. We get cis products versus trans products. Right? Between those two, which would be the more stable or likely product? The trans ends up being the most likely. So in the top reaction, we see the trans product. In the bottom reaction, notice they didn't show the trans product. Well, why not? If the trans is more stable and more likely to form, why did they not show the trans product for the bottom one?
Isn't it cis?
It is cis. Why did they show the cis?
There's still a chance of the product.
Right.
The trans is above it.
The trans isn't above it, because remember these are two different starting materials. So for the bottom one, why did they show the cis and not the trans? Because it didn't make trans. Okay. It's kind of a weird statement and now a weird question kind of in retrospect. Okay. We can't make the trans with the bottom reaction. Okay. Well, why not? Okay. In an E2, we're doing effectively the same kind of concept as the SN2. It's still a backside attack. Okay, but it's not a backside attack by the nucleophile. It's a backside attack by the electrons of the hydrogen that are getting removed doing a backside attack on the leaving bromine or on our leaving group. And if we look at this structure, there is only one hydrogen that we could remove. Okay? That single one hydrogen that is removable is already in the backside, so that if that goes through and occurs, great, we do the elimination. There is no way I can get the phenyl groups on opposite sides. Because to do that, I would have to rotate that bond. But if I rotate that bond, the hydrogen in the leaving group aren't on opposite sides. We can't do the elimination. Okay? So the E2 still has the same requirements of the SN2 in that we have to do a backside attack. Where this becomes trickier is that it's not a nucleophile. It's the hydrogen that's getting removed. Okay. Why does that need to happen? Well, there's a couple answers that we can use. Okay. One could be looking at molecular orbital theory. How many people want to see that? Okay. The other option is kind of the hand-wavy option. What is removing that hydrogen? The base. Okay. That base is supplying a whole bunch of electrons, negative charge. Okay. It has to come in and remove that hydrogen from as far away from the leaving group as possible. Why? There's an electron repulsion. The leaving group is leaving with electrons. If the OH came in on the same side as that leaving group was leaving, what happens? They repel and we don't end up doing the elimination. Okay? So we have to have this proper orientation. What is that orientation? What is the relationship between the hydrogen and the bromine in this structure? Okay. It is anti. Okay. You mean Newman projections? Yeah, I mean Newman projections. Okay. So we'd have to look at a Newman projection to fully see and appreciate that elimination. Okay. And that's what this slide is looking at. When we look at that same structure at the top, and we rotate it 90 degrees. Okay. Notice the CH3 part of this. This piece is going backwards. This piece is coming forwards. Okay. That methyl, or that's not a methyl, that phenyl is wedged coming at us so that if we did that rotation, it would now come in on the left-hand side of our structure. The hydrogen on the right, the bromine straight down. We do it with the same deal with the back part, and we get the alignment that they've got shown. Now the bromine and the hydrogen are anti to each other. Because of that alignment, we can do the elimination. Once the elimination occurs, I'm now locked into that orientation. Okay? Because of that orientation, when I go through to make then the final product, those phenyl groups, in this case we picked the top one, not the bottom one, would be locked in as the trans. Everybody kind of see that? If we did a Newman projection rotation with the back, and aligned the hydrogen to be staggered the other direction, it would be gauche. That would change the orientation of the phenyl groups with each other, with respect to each other, but I can't do the elimination now. as the nucleophile or the base comes in, it would be repelled by the leaving group. So we can't do the elimination. If we continue to rotate, we stand up with the other Gauss structure. Again, can't do the elimination. Okay? So you'll hear reference to this anti-alignment being super important. Okay? Why do we add this extra word to it? I don't remember, but there was some kind of reasoning behind it. Ultimately, antiperiplanar is the same thing as anti. Okay? What we're saying is to run an E2 elimination, the hydrogen and the leaving group must be anti to each other. So on opposite sides of the forming pi bond. Okay? Why is this not a problem for the E1? I don't quite accept two steps.
Can we go back a second?
I have a question about the repulsion between the leaving group and the base. So
Okay.
that staggering doesn't have anything to do with the attraction between the leaving group and the hydrogen. It's just you have to have that anti-staggering because of the repulsion between the base and the leaving group.
So there are two explanations behind why we have to have the anti-configuration. So this is the one that allows for the elimination. Okay, that one is absolutely true. Okay, we have to have that. The argument that I went through and gave, because nobody liked the molecular orbital theory argument, which is understandable, is that that base has to come in from the opposite side as the leaving group leaves. Because if the base tried to come in from the same side, what happens? Those electrons butt up against each other, and that chases the hydroxide. The second or the more mobile group chases it away. So we can't do the elimination. Right? So if we look at our Newman projector, that can help us see that. The hydroxide has to come in from the opposite end. Does that answer your question?
Yeah, I was just concerned about the attraction of the leaving group and the hydronium ion.
So what you're asking about is once it leaves, we would have H2O and Br minus. And you're wondering about that attraction.
No, before that. Like if they're Gauss and the base comes in, you're saying that the repulsion between the hydroxide ion and the leaving group bromine is stronger than the attraction between hydrogen and bromine.
Yeah.
Okay.
So the interaction between the hydrogen and the bromine is almost non-existent.
Okay.
Why is that one almost non-existent?
Or else they wouldn't be on that molecule.
Wouldn't be on there. Possibility. Okay. What else is happening in that Gauss interaction?
Serotonin rings.
That shaded area is electron repulsion of those two large groups, pushing away from each other. Okay? So the interaction between the hydrogen and the bromine, let's say let's just say, hey, there is one there. Let's call it that orange interaction. Okay? What have we built there? That's a really weird question. Okay, well, if we undid our structure to get it to that orientation, we're looking at something along these lines. I don't remember where all those pieces were. So let's just say it was this. That was our phenyl, and that's our CH3. What you're talking about is this attraction there. Okay. What have we built there? It's a really hard question. There's one atom, two atoms, three atoms, four atoms. What have we built? A cyclobutane. What can you tell me about cyclobutanes? They're highly unstable because bond angle strain. Right? So if there was even a partial attraction between that hydrogen and the bromine, what is that distance going to be? It's going to be really, really large because they're sp3 atoms. The likelihood that the bond angle would shrink down to even get them close enough to interact, virtually none. Right? So that interaction is not likely to happen. It is very rare to end up with four-membered transition states, and that's what we're talking about in your description there. Okay? Not a good thing to go through and draw. It can happen, just not very likely. Okay? So, back to my question, E1. Why is this not a relevant issue for the E1? The leaving group has already left in the first step. So if we look at the clutch stage where I can no longer do rotation, if I was to draw out my Newman projection, there's my phenyl, there's my methyl. Whoops, already forgot. Phenyl, hydrogen, hydrogen, leaving group. But here's the problem, the leaving group left. Okay, so it's no longer there. So I have to erase all those kind of pieces. Okay, well, if I erase those pieces, cool, that worked. How many groups of electrons would be around that carbon? That carbon being that purple one in my Newman projection. Not 2. There'd be 3. 1 being the carbon in back, the circle. Where's the other 2? We have the hydrogen and the phenyl group. This is trigonal planar. Those are moving directly out from the sides. Why do I not care about the orientation of the hydrogen? What's reacting? An empty p orbital for the carbocation. The hydrogen just needs to be somewhere on that axis. It can be anti. It could also be on the same side, because all I would have to do is rotate that structure. I'm allowed to rotate it because there's no double bond yet. It's only once that hydrogen is pulled off. Well, which conformation is going to be more stable, where the phenyl groups are on opposite sides or on the same? Opposite sides. So there's a barrier to the rotation. The elimination happens this way, where we get that trans product. Okay? It is a tricky thing to visualize because a lot of it comes back to those orbitals and how those orbitals align. Okay? This is where we should just kind of consider E1, we're forming a carbocation. Both products are possible, though trans is favored. E2 gets one product. Kind of like what happened with our SN1 and our SN2. SN1 gave us one product, SN1 gave us 2 products, SN2 gave us one product. Okay? And it's all to do with how those attacks happen. Okay? And even with that statement, we have to be careful because we're really getting to attacks, not necessarily to products. Okay? So, E2, the biggest thing that we really have to be concerned about is this antiperiplanar. Okay? Because one of the other things that we remember from our elimination is we want the most stable double bond. Okay? So we may have a structure that looks like it generates a stable double bond, but under E2 dynamics, I can't make that product because they aren't anti. Okay? So the E2 really focuses on that anti-alignment. You have to have that. E1, make the most stable double bond you can. Okay? Can I get mixtures? So here, I just said E2 only gets one product. Well, here, what is this showing? 2 products. So did I just lie on the previous slide? No, I didn't lie. Okay. What is now different about this structure from the previous reaction? This has 2 potential hydrogens to remove. If you go back and look at the previous reactions, how many hydrogens were possible to be removed from this structure? Only 1. So for that single hydrogen elimination, I get 1 product. When I move to this reaction, what happens? There's 2 hydrogens. For each of those 2 hydrogen eliminations, I get 1 product. That's why I'm seeing 2 products come out of this. Okay? So our eliminations can become extra tricky because there's usually tons of hydrogens, which means we have to be a little bit more careful about what hydrogens we're removing and when we remove them, and then what products do they produce. Okay? So there's lots of things that stack into that. Okay? The other thing that comes in here is, notice I'm saying a mixture of diastereomers can form. Why not always? Well, what if we ended with a product that didn't have cis-trans isomerism? Well, then I wouldn't have a mixture of diastereomers. Okay? So we have to be careful making blanket statements saying, well, SN1 always produces two products, okay? Or always produces enantiomers. Okay? And SN2 only produces one product. Depending on the conditions, you can see varying things come out of it. Okay? So don't make blanket statements about the reactions. Understand what the reaction does, draw the products, and then evaluate what is the relationship between those products. Okay? That extra step in drawing things out will ensure that you get the answer more likely than not. You can run through all those conditionals. Okay? If you try to just blanket memorize, you will encounter lots of problems. Okay? That, for the most part, is the end of Chapter 8. Okay? So in Chapter 8, what they go through and say is, this is a reaction. It is SN1. Do it. Okay? So we addressed those complications when we looked at each of those mechanisms. Okay? So we have to watch out for specified stereochemistry, potentially add some curved arrows into those, but for the most part, we just have to do what we're told to do. Chapter 9 becomes much more difficult, because what do we do in Chapter 9? Now, we don't tell you which mechanism it is. We don't even tell you which reaction it is, substitution or elimination. You're responsible at looking at all the pieces that contributed to these and trying to organize that information to say it is SN1, that means this is the result. Or it is SN2, which means that is this result. So you have to do a lot more predicting in your abilities. You have to understand what's happening there. Okay, so it becomes significantly more difficult. One of the things that can help you with this is consider your mechanisms. Okay, consider the conditions in it. Okay, do you think you're going to have a carbocation? Well, if there is a carbocation, think about rearrangements, because that could mess with your products. Okay, acid-base steps. Okay, this goes back to the leveling effect. Look at your reaction. Does it say it's running in hydroxide? Okay, if it does, don't form an acid. Because if you form a strong acid in a basic environment, you're conflicting with those given pieces of information. So we have to be a little bit careful with that. Okay? A quick kind of assessment we can do. What symbol, yeah, that's close enough, would we expect to see for a strongly acidic environment? Plus, okay, hydrogens, H+. Okay, those are strongly acidic environments. So what charge, if you were going to draw out the mechanism, should not show up? A negative. Why? Because there's a bunch of positive in the solution. There's no reason to make a negative. Okay? So this might mean you have to add an extra mechanistic step to prevent the formation of that negative.
Acid reaction?
That was for the acid reaction. So what would happen if it was a base reaction? What would you expect to see in the base? Negative. So what should never show up in your mechanism? Positive. Okay? So if you can limit some of those things, that can help you adjust through your mechanisms appropriately. The last big one to watch out for, which we kind of already addressed with the hydrogen and the bromine with the E2, intramolecular reactions are insanely rare. Okay? So if you're like, oh, I need to remove that hydrogen and put a hydrogen on, okay, at a different place in the structure. Well, I'm just going to have it all happen at the same time. Okay? Or with the same atoms. Be careful with that, because typically what happens is you're going to end up forming a 4-membered transition state or a 3-membered transition state. Okay? Those are unstable structures that aren't likely to happen. So if you're seeing two things that need to happen on a structure, treat them as independent steps. Okay? That can help you ensure that you're getting the correct mechanism out of it. Okay, so basic elements for both substitution and elimination. You have a substrate, you have a leaving group, you have a nucleophile or base, and you have a solvent. Okay, this should look pretty familiar because this was our basic structure for all of these. Okay, this should also look familiar because it's color-coded, and it looks like 4 separate topics, kind of like 4 separate videos that everybody's gone through and watched. I'm going to guess that awkward silence means you probably haven't watched them, in which case you're going to have a really hard time with these topics because we're not going to spend time on them. Okay? Let's ignore that. No, because I already ate lunch. Substrate classifications. Okay? We have our zeroary, primary, secondary, and tertiary. Those are going to be important, quick classifications to go through and evaluate. Okay? So you need to be able to think about them quickly. Okay? When you look at a substrate, primary. Look at a substrate, tertiary. Look at a substrate, that's primary with resonance. That's a harder one to see, but you should be getting to the point where you can recognize that resonance option. Okay? If we looked at stability, you're familiar with all that, so I'm just going to kind of slide through it. How is this going to affect our substitution reactions? Okay. Would I expect all of these to react according to SN1? What does SN1 mean? Leaving group leaves, then nucleophile attacks. That's perfectly valid. That's a lot of words. I want less. Unimolecular is not bad, except that's too fancy of a word. Carbocation. How do you get a carbocation? The leaving group left. That's part of it. Okay. Why do I not care about the nucleophile? Because it's unimolecular, and the nucleophile isn't involved in that rate limiting step. So I'm only concerned about the carbocation. So when I look at these, can I make a stable carbocation? Yes. Yes. No. Why?
Because the middle one is SP2.
Resonance. Resonance. SP2. How many of you know what those answers or those whys, what those whys mean? Okay. So when you write an answer on a test and say, well, this one doesn't react because of SP2, guess what you just told me? You have no clue what you're talking about. Okay? Because nobody said, I understand that. So when you write SP2 for the reason why that second one doesn't react, what's my response going to be?
Why?
You don't know why. Okay? Why? So what do those words mean?
There's more than one outcome.
Okay, which one you want to look at? First, second, third? I'll give you any two. Second. Okay. Why is SP2 relevant? If I remove that electron, what would happen? Or that leaving group? I form a positive charge there, right? Why is SP2 relevant? Secondary carbons are not necessarily SP2.
He's not as stable as tertiary carbon.
What happens is you have less hybridization. You become more electronegative. The more electronegative you are, can you stabilize a positive charge? No. There's your explanation. Okay? So it's recognizing that tie back. Well, where had we heard that explanation before? Unit 1. Okay? That's where it showed up. Here's where it comes back to bother you. Okay? The hybridization explains that I can't stabilize that carbocation. It gets even worse because what's the hybridization in the cation? SP. It's now even more electronegative and you're trying to put a positive charge on it? Not only put a positive charge on it, but also no octet. Okay? So everything about that structure is screaming, this is horribly a bad idea. Okay? So if you look at a starting material with sp2 hybridization and in your leaving group, you do not remove the leaving group from that position. Okay? Multiple choice, who cares? You don't have to explain it. You just look at it, sp2, I don't do it. Okay. Second one, what do you want? First or third? Okay, first one, resonance. What are we talking about? What do we need to do? Show the carbocation. That's a primary carbocation. Those don't form. That's awful. Bad job. Bad Mike. What's the problem with that? Okay. We can get extra fancy with our wording, okay, which is why it showed up in the lab. That is actually an allylic carbocation, referencing the position here that we have resonance. Okay. And this is where people, well, it's still positively charged. It is, okay, but only one carbon can react at any given instant. So which carbon do you want to react, the leftmost or the rightmost? Rightmost, I agree. Let's look at that carbon. Okay, what is the charge on that carbon? Sure looks like it's a +1, but remember, I'm only evaluating the purple structure. Is the purple structure the only structure for this compound? No, I also have to consider the red one because resonance. When I bring in the red one into this argument, what is the charge now on that carbon? Well, there it's 0. So if I now average the charge across those two structures, I get an effective positive charge of +0.5. Is that more stable than a +1? Yes. Is that more stable than the tertiary? Yes, because the tertiary has a +1 charge. So resonance is a stronger effect, and we can see that by drawing out those structures. Okay? This again goes to how we can test in OChem and how you can answer test questions. In a straight multiple choice, you could just say resonance done. You don't have to worry about it. Okay? If you're asked to explain, you have to evaluate the structures. Okay? There are multiple choice questions that could be set up in such a way that you have to be able to draw out these results to predict those potential products. Okay? If you don't draw them, you don't see those results. If you do draw them, you can potentially pick up the resonance and predict those products. This is why you should draw them. Okay? You are much better at analyzing things that are written down than you are at analyzing things inside your head. Okay? Get out of your head. Okay? Leaving group ability. I'll look at that structure. Which is the worst one? No. I'm going to bet that H is the worst leaving group. Why would that H be the worst leaving group? Okay, as a leaving group, it removes the electrons and it becomes H-. Okay. Why would H- be worse than OH-? They both have the same charge. But when I move to size, oxygen is larger than hydrogen. So oxygen can better stabilize that. Right? How about chloride? Okay. If I compared chloride to the oxide, they're both negatively charged. So we'd move to size. Chloride being larger than oxide can stabilize that charge better than the oxygen. It's a better leaving group. Okay. So the argument that we're using here for our leaving group ability is going back to and evaluating what is a leaving group, takes electrons with it, which means it has gained electrons, which means it is likely becoming negatively charged. I then have to evaluate stability. How do I evaluate stability? Charge, size, electronegativity, resonance, induction, then we can deal with hybridization. Okay? Those 6 things are critical to evaluate when you're looking at how a reaction occurs. Okay? And it is not just saying I want to look at resonance. Right? Resonance may be a moot point if there's a difference in size. So go through them in that order. Do you not have them memorized yet? You should do that very soon. Okay? So, some of the big words that kind of come out of this, I don't know why they decide to scale away from those same rules, but they do. They tend to be electron withdrawing. You mean electronegative because they can hold their electrons? Yes. Right? Weakest base, once left. Well, go through and evaluate weakest base. What do? Charge, size, electronegativity, resonance, induction. You apply all the exact same rules. Polarizability is a really fancy word for saying it's big. Okay? The bigger it is, the more polarizable. Those electron clouds can shift all over the place. Okay? And that is leaving group. Solvent. Okay? We've talked about solvents. Okay? What are the roles of our solvents? Well, first one, they have to dissolve everything. Okay? Because once they're all in the same phase, they can actually react. So if they aren't in the same phase, they don't react. After that, those solvents can be used to stabilize or destabilize certain reagents or intermediates. Okay? We would find out how they would affect those reagents or intermediates by... Does anybody have any doubt about what you should do? Because if you had some doubt, you know the answer. You should draw it out. Okay? Once you've drawn it, then you can start to evaluate where the charges are and how those things could affect each other. Okay? What are the classifications for solvents? Polar and nonpolar is an initial good place to start, though it's not the greatest. Protic and aprotic. Okay? Because those are now specifically looking at hydrogen bonding. We can now add in the concept of polar and nonpolar. We end up with protic, which by definition is polar. We end up with aprotic, which could be polar or nonpolar. But if it's nonpolar, by definition, aprotic is nonpolar. So we get three classifications. Protic, polar aprotic, and nonpolar. So only three answers. 33% of the time you're right. Okay, let's try and get it better than that. Think back to each of the mechanisms that you draw out, and what do you want the solvent to do? Okay? Number one, it has to dissolve everything. Number two, does it stabilize or destabilize certain reagents or intermediates? If it stabilizes an intermediate, that increases the likelihood for the reaction occurring because you're actually moving forward. The intermediate's a step along the way. What if it stabilizes a reagent? What would happen to the energy if you became a stable reagent?
They won't react.
It goes down, which then means the activation barrier goes up and they don't react. Right? So a blanket statement of just stabilize things doesn't help. Right? Just a blanket statement of destabilize things doesn't help. Okay? You have to be evaluating each of those mechanisms and the conditions that affects them, right? Which is tricky to manipulate. Okay? So, what do we got? Bunch of solvents up here. I even threw in some abbreviations for those names that you might typically see pop up. Okay, what do we think? First one, benzene. Okay, probably nonpolar. Why? Carbons and hydrogens generate nonpolar covalent bonds. Carbon to carbon is nonpolar covalent bonds, which means nonpolar solvents. There's nothing polar within it. DMSO. It's probably polar because we see an electronegative element. That's usually a big tip-off that we're looking at a polar solvent. Is it protic? Does it have a hydrogen bonded to oxygen, nitrogen, or fluorine? No. So 2. Why do we write it as DMSO and not as the full structure here? It's too long of a structure and it's too long of a name to write out, so we just write it as DMSO. Okay? You will very commonly see DMSO written out because it is your classic aprotic solvent. Methanol. Okay, it is polar. Big tip-off, we see the oxygen. It is protic because we see that hydrogen next to it. DCM. Okay. We usually get a couple answers in here. It usually runs the gamut between 2 and 3. It is polar. Why is it polar? Because chlorine is an electronegative element. So it is a polar solvent. Okay. It is aprotic because there's no hydrogen connected to oxygen, nitrogen, or fluorine. Last one, acetic acid. Okay. This one should just be screaming at you protic because it says it's an acid. That is the definition of protic. Okay? Once you've got them classified, you can then think back to the individual reactions that might have an effect on. Okay? Should we look at an example?
How come for DCM the dipoles don't offset?
The dipoles don't offset because the structure is not this. There the dipoles would offset with the electronegativities pulling against each other. They don't offset there. Okay? What we've drawn there is a Lewis structure, which doesn't work. So let's switch this up to a slightly different format. I could have just as easily have drawn it this way. Do the dipoles offset here? No. Do they offset somewhat? Yeah. If I look along that axis, one pulls that way, the other one pulls that way, and we do a vector analysis. They do offset a little bit, but not perfectly. Why am I drawing it out nice and flat like this to show that? Because that's easier to see. What happens when we move up to actually DCM? That's not planar, it's tetrahedral. And we look at the drawing there, that's not the easiest to pick up, but let's see what I can come up with. You guys aren't nice. Hydrogen, my wrist is the other hydrogen. Okay. And then I have a chlorine coming at you and a chlorine going away. Everybody kind of see it? This kind of hurts, by the way. Okay. So the chlorines counter each other on the axis that's aimed at you. Because one's pulling out, my thumb, the other one's pulling in, right? Are they countering on the up axis? What's countering against them? Hydrogens. Chlorine's more electronegative than hydrogen. The net dipole would be pulling upwards in the plane of the paper. Does that make sense?
Yeah.
Ow.
So the hydrogen was where that chlorine is on the top of the wedged, would that be?
So, you're suggesting we try this?
Would that be more?
That's going to be the same deal, even harder to visualize, but all that is just a change in the orientation of the structure, but it's still going to end up with the same issue. In this case, your dipole would be aimed opposite the hydrogen. Okay. It would be aimed in the plane of the paper that way. And actually not in the plane of the paper. It's going to be slightly going away on that one. Okay. So you have to be familiar with the terms used for the names of your acids. If during a test you see DMSO and you're like, I don't know what DMSO is, that's cool, raise your hand, ask. I might be like, you're supposed to know what that is. And you're like, yeah, I know. And I go, okay, fine, and I'll draw it up on the board. Okay. I almost always try to include the structure name for our solvents, both the formula, or sorry, this, what do we call that, name, symbol for it, and the structure, because I know most people don't memorize them. I know I never did. The ACS sometimes is kind about that, sometimes not. So it's a good idea to get used to starting to memorize those common solvents. Okay? So let's take a look at some things that could show up. If I want a solvent to dissolve a salt, what solvent should I choose?
Water.
Water doesn't count, that's too specific. 3 classifications.
Polar protic.
Polar protic, because water is a protic solvent. Right? Which solvent would stabilize a leaving group? Oh, that's a harder question. What is a leaving group? It takes electrons from the structure, so our leaving group is probably going to be negatively charged. Okay? What solvent would do best at stabilizing a negative? Well, what would stabilize a negative? A positive. Which of our solvents generates the most positive atom? A protic. Okay? So stabilizing a leaving group, a protic solvent might do best to stabilize that, because it's going to help neutralize that charge. Okay? What type is bad for nucleophiles? What the hell is a nucleophile? Okay? So, nucleophile, we're going to address this definition again. Okay? Nucleophile. What does nucleophile literally break down to?
Proton loving.
It does not break down to proton loving because it says nucleo.
I didn't say free.
It's okay.
It loves protons.
It is nucleus loving, and this is where and this is my fault. I'm not yelling at you. I'm yelling at me. Okay? Nucleus loving. What is in a nucleus? Protons. The subatomic particle of protons are found in the nucleus. Right? That gives us a context of what the nucleophile is attracted to. What does that mean the nucleophile is? A negative. Okay? It donates electrons. Okay? So it would be negative. It donates electrons to what? And this is the issue I have with the proton-loving statement. Because that would sound like it would donate to
No, it doesn't.
protons. No, it doesn't. What does it donate to? Nuclei that are not protons. Wait, what? What is a proton? A hydrogen with no electrons, right? So all of the atoms on our periodic table are made up of hydrogen? No. Guess what proton references? 2 things. Proton references the atom of hydrogen, missing an electron. It also references the subatomic particle of a proton. Those are 2 different things and have different meanings. When we're talking about a nucleophile, you're talking about donating electrons sort of to a nucleus, okay? Not to a proton. What species donates electrons to a proton? A base. Okay? So we have to be very careful with what those words mean and what those definitions are. There are 4 primary classes of reactants that you should memorize: nucleophile, electrophile, base, and acid. Those should be memorized. Okay? And they should be memorized using the fewest words possible. Okay? Not because I don't want you to be wordy and use big words, but the fewer the words you use, the less likely you'll make a mistake. So a nucleophile is donates electrons. Okay? An electrophile accepts electrons. A base accepts protons. Okay? And we're using the proton there in reference to the hydrogen, and we're really trying to use that word, okay, because it helps us differentiate the base from the nucleophile, because they have very similar reactivities. Okay? And an acid, a proton donor. Right? So we're really just spinning those definitions around and keeping them in mind, because when I'm asking which type of solvent is bad for a nucleophile, you need to know that a nucleophile donates electrons, which means it's negatively charged. Okay? What would be bad for a negative charge? Okay? To donate electrons, what charge does it need to be? Negative. What would make it less likely to donate those electrons? If it wasn't negative. What solvent would cancel a negative? A polar protic solvent. right? Because the protic solvent brings in a very large positive hydrogen. That can cancel that charge. Right? So we're using those solvent classifications and thinking about the definitions of what those pieces are to be able to apply them forwards. Okay? This is an extra fun slide. And by extra fun, I don't like it really at all, but it's got a lot of information on it. Nucleophiles have donatable electrons. Okay? Lone pairs or pi bonds, but for the most part, lone pairs. Okay? They are typically negatively charged. Okay? And if they are negatively charged, they are stronger than the neutral counterpart. Why might that be true? The negative, or a nucleophile, needs to react with something, right? So it needs to be less stable. What's the first thing I would evaluate on my stability list? Charge. You mean a negatively charged nucleophile is more reactive than a neutral? Yes, for the exact same reason we used that list. Okay? Nucleophilicity decreases from left to right. Okay? We're now looking at left to right, which is really a way of looking at electronegativity. This gets a bit weird. Why would this get a bit weird? Because according to our rules for stability, we start with charge, and then we move to size. Left to right, what happens to size? Nothing. Okay? Size really has no effect left to right. What are we talking about when we look at this rule? Electronegativity. Why did I skip size? Because size effects when it comes to nucleophiles have a very strong solvent dependence. That solvent dependence pretty much throws a massive monkey wrench in anything we would do to go through and analyze them and makes it insanely difficult to interpret. Okay? So insanely difficult that I usually have to spend a good solid 10-20 minutes reviewing it to make sure I've got it straight in my head before I move forward with it. Okay? This is why slides are awesome, because I can just turn and look at the slide and be like, if it's in a polar protic solvent, the bigger it is, the more nucleophilic it is. Okay? I can literally just read the answer off the slide. Okay? Polar aprotic, smaller are more nucleophilic. If there's no solvent, we assume bigger is more nucleophilic. Okay? So the size for nucleophiles ends up being really kind of counterintuitive to a lot of our interpretations. Okay? So let's go to the no solvent one, because let's try and keep it simple. It's saying bigger is more nucleophilic. Okay? Which is kind of counter to what we talked about, right? The bigger it is, the less likely the electrons are found at any given point, which means less reactive. And yet, what is this saying? It's saying it's more nucleophilic, which seems a bit weird. Okay? The reasoning behind this is because it is bigger, that electron cloud can distribute, that's a better word, distribute a little bit more accordingly around your electrophile. Okay? Meaning the electrons can shift to one side of the molecule a little bit easier than the others, making it easier for it to share electrons. Okay? When we move up into the solvents, now things get a bit wonky on us. Because what are the solvents doing to our nucleophile? I can kind of accept changing it. They're potentially stabilizing it. Okay? So that stability now changes our interpretations of what's happening within them. Okay? So let's go through and take a look at a protic solvent first, the one up top. Okay? Protic solvents have very large hydrogens, or positive hydrogens. Okay? And if I look at the protic solvent, what happens? Very large partial positive means it needs to get neutralized. What's going to neutralize it better? It is the solvent, so no. A negative. Something more negative is going to stabilize it. What is special about the chloride in comparison to the bromide? It's more electronegative, meaning it is more negative. So what happens in the protic solvent? We get a very strong attraction between the solvent and the nucleophile. Right? That strong attraction means it is a weaker nucleophile. So if we double back to our answer, polar product, bigger was more nucleophilic. It's actually not making the bigger one more nucleophilic. What's happening is the solvent is stabilizing the smaller one. It has a stronger attractive force between the solvent and the nucleophile. For the nucleophile to react with anything, what has to happen? It has to break those solvent interactions. What? Yes. Believe it or not, it's true. Okay. Each of those interactions has to get broken before the nucleophile can react. Because bromide is so much larger, it has and less negative, it holds a weaker bond to the water molecules, which means easier to break the interaction, which means more likely to interact with our substrate. So the larger one becomes more active as a nucleophile. Not necessarily more nucleophilic, but more active as a nucleophile. The result being, larger appears to be more nucleophilic. What happens when we switch solvents? Now in the bottom case, we're now aprotic. And in the aprotic situation, what happens? We have a much smaller partial positive. Not only is it a smaller partial positive, that positive is found on an atom other than hydrogen. That atom is typically found in the middle of the structure. So we've now broken the opportunity for even making decent attractions between the solvent and our nucleophile. Okay? Why is that important to us? That means if we look at the smaller one, I get fewer solvent molecules around it than I do for the larger one. And because they don't have an attractive force to each other, it's now just the quantity of solvent that's there. The larger one has more solvent around it. For that nucleophile to react, what has to happen? It has to get more of the solvent out of the way. More stuff in the way means less likely to happen. And what happens? The chloride becomes the stronger nucleophile. Okay? You get this really weird dynamic with it. It's not easy to interpret, and it takes time and practice to manipulate. Time and practice that even I, admittedly, haven't spent the time to work on. Okay? So at best, you can get one question on dealing with the solvent effects on nucleophiles. Okay? It is not an easy one to manipulate, and it is typically not tested on because of that. Okay? Which gets us to really the last point on that slide, which really shouldn't have been under harder because it's kind of a really important thing. Number 5, steric hindrance. The less atoms around your nucleophile, the more nucleophilic it becomes. Why? What is the nucleophile reacting with? The substrate. Where in the substrate? With a positive charge. What positive charge? Typically carbon, and not hydrogen. Because if it reacted with the hydrogen, it wouldn't be a nucleophile anymore, it would be a base. Okay? So the difference between nucleophiles and bases really hinges on this last definition here, or this last relationship. Okay? The smaller your negative charge, the more likely it will act as a nucleophile, and the less likely as a base. And all this has to do with what the nucleophile and the base are doing. The base is reacting with hydrogens found on the outside of a structure. Nucleophiles are reacting with not hydrogens, all the stuff found inside the structure. Right? And this is a horrible analogy. Which would you rather have shoved through you? A needle or a sword? Yeah, I know. It's a bad analogy. That's a really big needle if it's even coming close to a sword. I mean, come on.
That's what I said. It depends on the size of the needle.
We would probably prefer the needle because that'll pass straight through us without a big deal. What's the sword going to do? It's going to cut up everything on the outside on the process of it passing through. That's not going to be so pleasant. Okay? The sword's going to destroy the outside very quickly. The needle doesn't. Okay? Same thing's happening with our nucleophiles and bases. The base is reacting on the outside. Okay? The nucleophile needs to react on the inside. Okay? And because it's reacting on the inside, it has to avoid all of the outside stuff. Okay? The only way it can do that is if it is small. Because if it is large, it impacts the outside first. Right? I said it was a very kind of tenuous thing. So let's take a look at the two here. Or, sorry, this one. What would you expect that negative charge to act as? Okay? It's kind of small. It's just a single atom, right? Okay? It could probably come in and attack there. Kick out the leaving group. Okay? Couldn't it also remove a hydrogen? Yeah, that species could act as both the nucleophile and the base. Because it is smaller, we might be trying to lean towards it acting as a nucleophile preferentially. Right? But it really has both options available to it. What happens if I switch to this structure? Right? This structure is still that negative oxygen, but what's all the rest of the stuff attached to it? A bunch of electron density. So if this oxygen tried to get in to react with that carbon, what happens? These things butt up against each other, preventing the nucleophilic attack. So it can't act as a nucleophile. So what does it do to neutralize that negative? It goes to the hydrogen. Right? So the larger atoms are now exclusively bases. Okay? The smaller negatively charged species can act as both nucleophiles and as bases. Okay? It is insanely rare to get a large species to act as a nucleophile because of all that steric hindrance. Okay? That's how size affects these. And ultimately, isn't that something you probably already knew? Did you know the definition of a base?
Yes.
Did you know where the base reacted?
Yes.
Yeah. Did you know the definition of a nucleophile?
Yes.
Did you know where the nucleophile reacted?
Yes.
All we had to do was then go through and say, well, what do you think about these size things? Do those things interact with each other or not? Yeah? Okay. You drew the same conclusion. Okay? You have the ability to draw these conclusions. The hard part is recognizing where all those things are coming from. Okay? So what do you guys think about this guy? What was the laughter for? It's a nice little structure there. We can be extra irritating. Nucleophile, base, or none of the above. And it's extra, extra, extra irritating for another reason. You want to know how you figure out how it reacts? Of course you do. What am I drawing? Resonance. When we draw out the resonance, what do we see? What do you see when you draw out the resonance? We have a negative charge. This structure is actually a really good base. Okay? It cannot act as a nucleophile because that thing is big. Okay? Nitrogens are typically great as bases, okay, because they're willing to share those electrons. Okay? And we can add a bunch of steric bulk to them to prevent them from acting as nucleophiles. Okay? And in fact, what we'll learn in second semester is nitrogens as nucleophiles are horrible. Okay? Generally an awful idea. Okay? So, some common nucleophiles. We got some negatively charged nucleophiles, and we got some neutral nucleophiles. The only thing that's extra kind of special in this, or not only thing, because there's a couple in there, your chloride, bromide, and iodide will only act as nucleophiles. So if you only want a nucleophile, you should be using one of the halogens. Why do they not act as bases? This is one of the reasons why in Gen Chem you should have been told you needed to memorize your strong acids. Those won't act as bases because they're strong acids. The instant they acted as a base, they would immediately form a strong acid and immediately dissociate right back to where they started. Okay? So having some of that knowledge from Gen Chem can help you out. So, solvent effects for substitution. What's going to stabilize that cation? What would I need? Okay. I heard a suggestion for a nucleophile. That is an awesome idea to finish the reaction. I'm talking about a solvent effect here. I want to know what solvent I should use for the SN1. So we said there were 3 classes. Okay, we have our polar protic, and our polar aprotic, and our nonpolar. Which solvent is going to be best to stabilize that cation? Why the polar protic? What does the polar protic bring in? Okay. A very large partial negative. What can that very large partial negative do? It can stabilize that positive charge. If the positive charge becomes stable, what have we done to the likelihood of forming it? We've made it more likely, which means in an SN1, where I form a carbocation, I want a polar protic solvent. Okay? So we just double back to the mechanisms that you already know and say, how do these things affect your reactions? Okay? So let's take a look at some kind of mechanistic extras. Okay? These are all bad things potentially. So if we take a look at the reaction setup, okay, how might we go through and do that top one? Well, what changes as we look from left to right? Okay.
So we need to grab the box.
Okay. We formed an O-methyl bond, and we broke a CI bond, and we also broke an OH bond. Okay. So one option, I want to form that OH bond. So I'm going to do it. Okay, what's the result? Whoops. Don't forget your carbons. And I don't want a positive oxygen, so I'm going to take the electrons away. And I would end up with my product, right? And in fact, dude, I even have a base to remove that hydrogen. What is wrong with that mechanism?
It is a basic solvent, so we would have to have O-.
I'm in a basic environment forming a positively charged structure. Basic environment means the charges should be negative. That's not so good. Why else is this a bad reaction? I did not show a hydrogen bond to iodine, so I don't know what you're talking about there. I had OH remove the hydrogen. What mechanism did I show? SN2. How do you know what's shown as SN2? Strong base. So there's an interesting idea, bringing in what reagents are present. The issue with having a strong base in an SN experiment is I need a strong nucleophile. I don't want a base. In fact, if I had a base, what reaction was most likely to happen? An elimination. So I don't want a base. What I do want is a nucleophile, and I want that nucleophile to be strong. Okay? Why do I need a strong negative charge? I'm trying to chase the leaving group off the structure. Okay? I'm trying to chase that iodine off. I'm going to force it off by bringing in a negative to chase the iodine away. What kind of nucleophile do I have? It's a weak one. So I'm saying this is SN2, and yet my very first step, where I'm going directly into the SN2, I don't have the pieces necessary to run an SN2 reaction. So pretty much everything about what I've just shown is wrong. Awesome. Way to go, Mike. So try again. Fix me. Like, where to start?
So
Knock it off.
KOH will dissociate and OH minus will grab hydrogen.
Okay. So there's a suggestion with the KOH to show this as K plus and OH minus to dissociate. I would immediately show it as K plus and OH minus. I would even argue the mention of dissociate, while correct, I would not even mention because it's an ionic bond. I'm going to immediately get rid of it anyway. Okay. Now what did you want the OH minus to do?
It will grab the hydrogen,
It'll grab the hydrogen.
given a negative charge of oxygen, which will be basic in the basic environment.
Keep doing that. Now what could happen?
And then
Now it can do the substitution reaction. The order in which you do your reactions becomes very important when you talk about a mechanism. Okay? The first answer provided is wrong. This answer is now correct. You did the exact same things, just in a different order. Order is important. Okay? For anybody that likes to challenge that idea, put on your socks after you've put on your shoes. Okay? Order is important. What's going on with the bottom one? What do you see? Okay. Strong acid. It's not a bad observation. In fact, I would argue that's probably the best observation you can make, so we'll go ahead and star that. Okay. Really all I was asking for the changes from left to right.
okay, so here
Break the oxygen and hydrogen.
OH will grab hydrogen from the acid.
Which one?
No, from the bottom of H2.
Yeah, H2SO4. That hydrogen gets picked up by which oxygen? You said OH. Which one?
The structure, yeah.
They're both structures.
Will grab the structure.
Why the left structure and not the right structure? Hold on a sec. Hold that thought. I heard a quick suggestion because the substrate. Be very careful. You're making the statement that substrate shows up first. Take a look at the first reaction we ran. What showed up first? The nucleophile, not the substrate.
It's because
The sequencing in your reactions is not always substrate then nucleophile. It can be nucleophile then substrate. Be very careful with that. That is also a very common thing that students will mess up because they see it first and they assume substrate. It's not always true.
So you have to make it so the leaving group is more likely to leave. So if you made it so the hydroxide picked up H, it would be positive and it'd be more likely to leave.
You're telling me that's not more likely to leave than if I show the other one? So within those blue circles, you're telling me the top one is a less good water molecule than the bottom one. I'm going to challenge that water is water. Both of those are equally good leaving groups. Still my question, which OH?
I would say that the ring creates that electronegative cloud with the wrong electrons that surround it. So it pulls that hydrogen from the acidic solvent stronger.
So you're saying that this atom is electron withdrawing,
So
Because the ring?
creates the cloud.
creates a cloud that draws electron density towards it, right? Which would mean what charge would build on that oxygen? Someone said it. A positive, which would mean bottom structure is bad. And the top structure was good. Which structure do you think is right, top or bottom? Okay. That's a bit of a dilemma. You're saying the bottom one is right, the top one is wrong, but your explanation just told me the other way around. That's fine. You can still go with it. So let's try it this way, because maybe this is the next part of this. What would happen in the next step? The water's going to leave by getting those electrons, okay, which would generate CH3 positive, because water left with the electrons. And we're already hearing an ooh, no. Versus what's a more stable carbocation? The bottom structure is a more stable carbocation because? Resonance. So the bottom one makes more sense if we go through an SN1 reaction. How do we know we're going through SN1 to make a carbocation? And don't tell me, because you drew one. Yeah. Just because I drew it doesn't mean it's right. Why should I be drawing it as a carbocation mechanism? Say it again. How do I know I have a weak nucleophile? What would the nucleophile be in the red case? We would have our big, large structure, and it wouldn't be negative. It could never be negative because strongly acidic environment. Right? Which means it's going to have to be a weak nucleophile, which means I have to go through a carbocation, and the zero-area carbocation is crap. The red one fails as a mechanism. The bottom one wins.
So you're saying acidic environments always produce a weak nucleophile?
Yes. Acidic environments always produce a weak nucleophile. What do acidic environments bring in? Give me more than positive. H plus. What does a nucleophile bring in? Negative. What happens when you bring a negative near a positive? They cancel each other. So if we're in an acidic environment, an SN2 or a type 2 mechanism is a really bad idea. Okay?